Good morning, children. Up to in the previous class, we completed magnetic field induction due to a straight current carrying by magnetic field induction due to a circular loop and magnetic field induction due to a solenoid. And some applications also completed. Example problems also completed related to magnetic field. Now, we are going to discuss about Ampere's circuital law. Ampere's circuital law. The statement of this Ampere's circuital law is the line integral of a magnetic field. The line integral of the magnetic field be along a closed path. Along a closed path. Along a closed path. The line integral of a magnetic field along any closed path, is equal to the mu naught times of the net current enclosed by it. Line integral B dot dl bar is equals to mu naught times of current, net current. I means net current, mu naught times of I. See the statement of Ampere's circuital law is the line integral of a magnetic field due to any closed path is equal to the mu naught times the net current enclosed by the circular, not circular, enclosed by the closed path. It may be a circular loop or any shape of the body. It is maybe a circular loop or any shape of the body. See the statement of Ampere's circuital law is statement. Listen that statement. The line integral of the magnetic field due to any closed surface is equal to the mu naught times the net current enclosed by the circular loop. Net current enclosed by the circular loop, or net current across the area bounded by this. Integral B bar dot dl bar is equals to mu naught I. Here suppose this is the current I2 and this is the current I1 and this is the current I3 and this is the current I6 and this is the current I4 and this is the current I5. Here the statement of Ampere's law is the mu naught times the current enclosed by it is nothing but Ampere's circuit. Now here magnetic field induction B integral B bar dot dl bar is equals to mu naught times of the current enclosed. So inward current into the current means I1. Outward current, this is minus I2. This is also outward current minus I3 plus I6. This is about magnetic field induction B integral. Magnetic field induction B means magnetic field induction. Integral B bar dot dl bar is equals to mu naught I1 minus I2 minus I3 plus I6. Here you have some doubt. What about the current I5 and I6 is outside of the loop. Here outside of the loop, the currents, it may the magnetic field will becomes to 0. Magnetic field due to this I5 and I6 current is 0. So some points regarding to Ampere's circuital law. Points regarding to Points regarding to Ampere's circular law. Ampere's circular law. Ampere's circular law. So first point is the line integral does not means this line integral does not depend on shape of the closed path. Line integral does not depend upon the shape of the closed path. So here the second point is the current outside of the closed path. Current carrying by outside the closed path. Magnetic field is 0. The current carrying wire in outside of the closed path. Then magnetic field induction is 0. V bar is equals to 0. And third one is Ampere's circular law is analogous to Gauss law in electrostatics. Ampere's circular law analogous to Gauss law in electrostatics. Gauss law in electrostatics. We know that Gauss law. What is the statement of Gauss law? Intensity of electric field, line integral of electric field is equals to the net charge enclosed by epsilon naught. Net charge enclosed by epsilon naught. Integral E ds is equals to integral E ds is equals to Q enclosed by epsilon naught. Q enclosed by epsilon naught. Here this is the charge, this E bar means intensity of electric field. This Ampere circuit law is analogous to the Gauss law in electrostatics. Ampere circuit law is applicable for current carrying in straight conductors. This is applicable for Ampere circuit law is applicable for current carrying in straight conductor. Current carrying in straight conductors. Current carrying in straight conductors. Ampere circuit law is applicable for current carrying in straight conductors. This is about Ampere's circuit law. Once again, this is the statement of Ampere's circuit law. The line integral of a magnetic field along a closed path is equals to the mu naught times the net current enclosed by the area bounded by this. Area bounded by this path. Then integral B dot dl is equals to mu naught I. Then points regarding to Ampere circuit law is line integral does not depend upon the shape of the path. Second one is current carrying a conductor outside this loop, then magnetic field induction is 0. And third one is Ampere circuit law is analogous to the Gauss law in electrostatics. Then fourth one is it is applicable for current carrying in straight conductors. For next one, magnetic field induction or intensity of magnetic field near a long straight current carrying wire. The long straight current carrying wire, the magnetic field lines is a circular loops like this. Magnetic field lines. Magnetic field lines. So at the center of the circular loop P, the radius of the circular loop is R bar. Radius of the circular loop is R bar. Here according to Ampere circuit law, line integral V bar dot dl bar is equals to mu naught I. Here, current carrying in a straight conductor, magnetic field lines will be like this. So let us consider the element dl bar at this point, dl bar. And V bar also will be like this. This is the dl bar and V bar. Both are in the same direction. Means like angle between V bar and dl bar is 0. V bar and dl bar is 0. Therefore, according to the Ampere's circuital law, integral V dot dl bar is equals to mu naught I. Here integral V dl cos 0 is 1. Therefore, integral line integral of dl bar is equals to mu naught I. Line integral means it is this upper loop of line integral is 2 pi r. Means like this circumference of the circle. Then radius is r. Circumference of the circle is nothing but line integral. Line integral of a closed path. This closed path is a circular loop. Then the closed path length is 2 pi r. Means like circumference of this circle. Then V integral V on 2 pi r is equals to mu naught I. Then magnetic field induction B is equals to mu naught I by 2 pi r. Magnetic field induction B is equals to mu naught I by 2 pi r. That is the magnetic field induction. At this point, the magnetic field induction is, here not P. This is the P, which is at a distance r from the current carrying a wire. At this point, the magnetic field induction is a circular loop. Then magnetic field induction at B is equals to mu naught I by 2 pi r. Mu naught I by 2 pi r. Here r bar is must be less than, means like this r bar is here. R bar must be less than length of the wire. Length of the wire L. R is less than L. R is less than L. Ampere's circuital law. According to this Ampere's circuital law, let me consider any point on the axis of the current carrying conductor. At any point on the axis of the current carrying conductor, on the axis of the current carrying conductor, magnetic field is 0. At any point on the axis of the current carrying conductor, like here this point or this point, or you can consider any point, but magnetic field induction is 0. By Ampere's circuital law, B is 0 at any point along the axis of the current carrying conductor. And one more point is, magnetic field to a current carrying straight conductor does not depend on reference frame. Magnetic field induction due to a straight current carrying conductor. Current carrying conductor does not depend on reference frame. Does not depend on reference frame. And next point is Ampere's circuit law is applicable for symmetrical current. ACL, Ampere's circuit law is applicable for symmetrical current. Then Biot-Savart's law is applicable for asymmetrical current. Biot-Savart's law is applicable for unsymmetrical current distribution. This is a unsymmetrical distribution of unsymmetrical current distribution. This is about magnetic field induction near a long straight current carrying current. Let's say an application. The magnetic field due to a long straight current carrying conductor. A conductor of radius r carries a current I. I current carries a long straight current carrying conductor of radius capital R. This conductor carries a current I. This conductor carrying a current is I. Then current density of this conductor is J is equals to I by pi R square. Means current density is equals to current per unit area of cross section. Here area of this conductor is pi R square. We need to find the magnetic field induction inside of the current carrying conductor. This radius of this Ampere's circuit loop means R. Then this R is less than the capital R. So at this point we need to find magnetic field. At this point we draw a circular loop of the Ampere's circuit law. Then here inside I current is not there. Some current is I dash. Because of in the total current carrying a conductor of radius R, I current will be there. Now let me consider a point at this P. That P is R less than R. According to Ampere's circuit law, integral B dl is equals to mu naught I. I means net current enclosed by this path. This path enclosed by this path, net current is I dash only, not I current. I dash current is there. Here I dash is equals to J into pi small r square. I dash is equals to J into pi small r square. J means current density. Are you clear? I think this I current conductor area is pi r square, but I dash current area of conductor is small pi r square. Then cross multiplication we can take. Then current of Ampere's circuit law inside is I dash. I dash is equals to J into pi r square. Integral B dl Here integral V integral dl is equals to mu naught j. J means what is j? I by pi capital R square into pi capital R square into pi small r square. Pi small r square. Therefore, V integral dl. Integral dl means line integral. Line integral of the circular path is 2 pi r. V into the circular path is 2 pi into small r. 2 pi into small r is equals to mu naught I r square by capital R square. Square r get cancelled. Magnetic field induction V is equals to mu naught I by 2 pi r square into small r square into small r. Here I by pi r square is nothing but current density. We can write in terms of current density mu naught J by 2 into r. Then magnetic field induction inside of this straight current carrying conductor is directly proportional to radius of that circular loop. Radius of the circular loop. Then case 2. R is greater than R. R is greater than R. Means like this is the current carrying conductor. Current carrying conductor of radius R. The total current carrying this conductor is R. We need to find the magnetic field at this point Q. This small r is greater than r. Now we can draw a Ampere's circular law. We can take a closely curved loop. For this integral B dl is equals to mu naught I, means the total current is enclosed here. Total current enclosed. B integral dl. Integral dl means 2 pi r is equals to mu naught I. Therefore, magnetic field at outside is equals to mu naught I by 2 pi r. Here magnetic field is inversely proportional to r. Inversely proportional to r. Once again see this application. So that the magnetic field due to a long straight current carrying conductor. A long straight current carrying conductor of radius is capital R. Capital R. Then current carrying is I. Current density is equals to J by pi r square, means like current by area of cross section. Here two cases are possible. One is case 1, R is less than R. R is less than R means we have to draw a Ampere circuit law, means like a closed path at that point T. Integral V dl is equals to mu naught I dash. I dash means current enclosed in this loop. That current enclosed in this loop is I dash is equals to J pi r square. Then magnetic field at point P is mu naught J by 2 into R. B is proportional to R. Here case 2 R is greater than R. Magnetic field induction is inversely proportional to 1 by R. Magnetic field induction is inversely proportional to 1 by R. It means B varies inside the conductor is hyperbolic, and it means current carrying B varies inside is linearly, from outside is hyperbolically. Like we draw a current radius and magnetic field induction. We draw a radius and magnetic field induction. Inside it is a straight linearly. Linearly it is variable, means B is proportional to R. On the surface onwards it is hyperbolically. On the surface on it is hyperbolic. Then B is inversely proportional to 1 by R, dr is constant. Here B is directly proportional to R. This direction y-axis is magnetic field, x-axis is radius. Why x-axis is taken as radius means radius is independent value, magnetic field is dependent values. When we draw the graph, always dependent values are taken in y-axis, independent values are taken in x-axis. See children, everyone, here inside of the conductor from center to on the surface, B is linearly variable, means like straight. On the outside, on the surface to outside, B is hyperbolically it is variable. Hyperbolically it is variable. Let us see on another application. A hollow current carrying conductor. The variation of magnetic field. Let us see another application. The variation of magnetic field as a function of radial distance r due to a hollow cylinder carrying current. This hollow cylinder is carrying a current. Hollow cylinder of inner radius is A and outer radius is B. Then current density of this hollow cylinder carrying current is current density. J is equals to current carrying of this hollow cylinder is I. Current density is equals to pi of B square minus A square because of here radial distance. B inner radius is R and outer radius is A. Then area of this hollow cylinder is pi of B square minus pi of A square, means external to internal is nothing but area of this hollow cylinder. Then we can consider a point P in this hollow cylinder of radial distance is R. Let me consider a ampere circular law from this radial distance is R. Now we can take integral VdL is equals to mu naught and I1, means current inside of this ampere circular law is I1. Therefore, I1 is equals to I by pi of B square minus A square. Pi of B square minus A square into R square minus A square. Pi of R square minus A square. Only for current due to this small, like we see here, R square R square minus A square. Current due to that amperes closed. Ampere circuit law means only the current for this. How much current is there for this one is I1 current. I1 is equals to I by pi of B square minus A square into pi of R square minus A square. Then B integral dl, because of B dl bar angle is 0, cos 0 is equals to 1, is equals to mu naught I by B square minus A square into R square minus A square. Therefore, B is equals to mu naught I by integral dl means 2 pi R into B square minus A square into R square minus A square. B square minus A square into R square minus A square. This is the magnetic field induction due to a hollow cylinder current carrying conductor as a function of radial distance. As a function of radial distance. Now we can consider cases 1. R is less than A. This R is less than A means, like here, there is no current carrying this, then magnetic field induction is 0. B is equals to 0 because there is no current inside of this hollow cylinder. Hollow cylinder, there is no current inside of this loop. Where we consider Ampere circuit law, in that Ampere circuit law, inside of a closed path, there is no current carrying. There is no current carrying means there is no magnetic field. Magnetic field is here, 0. And case 2, R is greater than B. R is greater than B. Then magnetic field induction B is equals to mu naught I by 2 pi R, because we need hardly consider these areas. The total current enclosed here means like the radius R is here at this point. Then the total current enclosed in this loop. Total current enclosed in this loop means then magnetic field is B is equals to mu naught I by 2 pi R. Here R is less than A, B bar is equals to 0. R is greater than B, magnetic field induction B is equals to mu naught I by 2 pi R. See here, when we draw a graph between magnetic field and radial distance, B bar and radial distance, up to J, there is no magnetic field induction means it is a discontinued. This line is a discontinued because from center to at point A there is no line, there is no magnetic field. Means magnetic field where it starts on the surface, means then this is a discontinuous line. From on the surface onwards, again this is a hyperbolic condition. This is the application of magnetic field induction due to the Ampere's circuital law. Thank you for listening everyone.